For decades, turf management at premium facilities has been defined by volume. To manage stress and maintain playability standards, the standard operating procedure has been to load the property with bulk synthetic chemistry. This cross-section of a soil profile illustrates the physical bottleneck of that model. When large granular fertilizers enter the soil matrix, a massive percentage of the product never reaches the plant. It either becomes chemically locked up by binding to soil particles, or it leaches completely past the active root zone. Because so much efficacy is lost to the soil, operators are forced into a cycle of over-application just to meet the turf's baseline metabolic requirements. The soil becomes saturated, and only a fraction of the applied product is actually utilized by the plant. This inefficiency drives up every associated operational cost. Facilities dedicate hundreds of man-hours and significant storage infrastructure entirely to shipping, staging, and spreading massive pallets of bulk material. And as extreme heat waves and unpredictable rainfall become the norm, this legacy model performs even worse, accelerating nutrient leaching and compounding plant stress right when the turf is most vulnerable. The result is an economic trap. A facility's maintenance budget becomes directly tethered to the price volatility of global fossil fuel and commodity fertilizer markets. Relying on volume to force plant response creates systemic waste. Scaling up the same bulk chemical inputs is no longer a defensible operational strategy. The alternative requires moving away from the soil entirely. Using fourth-generation nanotechnology, we can replace commodity fertilizer loading with molecular precision. By utilizing these nanoscale biological protocols, facilities maintain torr-quality surface standards while reducing their total applied nitrogen footprint by up to 99%. Applying this same technology to moisture management yields similar efficiencies, cutting bulk surfactant fluid volumes by 90 to over 97%. Those numbers contradict traditional agronomy. To understand how they are achievable, we have to look at the mechanical data from recent field audits. Environmental stewardship and budget protection are the direct results of engineering extreme metabolic efficiency into the plant. This split-screen diagram highlights the mechanical difference between the two approaches. On the left, bulk applications rely on root foraging through the soil matrix. On the right, direct-to-cell nanotechnology is delivered as a foliar application, entering the plant leaf immediately. By shrinking elemental nutrients to the nanoscale, the product bypasses the unpredictable soil profile. The nutrients pass directly through the leaf stomata into the plant's vascular system. Without the interference of soil chemistry, nutrient uptake efficiency rises to over 95%. This removes the waste margins that require superintendents to apply hundreds of pounds of product onto the ground just to get a few pounds into the actual plant tissue. With immediate vascular uptake, the plant no longer has to expend vital energy foraging through toxic or dry soil to find nutrients. That metabolic energy is redirected entirely into structural cellular development. Once you achieve 95% efficiency, the inputs are measured in precise ounces rather than bulk pounds. Bypassing the soil layer is the specific mechanical change that decouples plant health from massive chemical volume. The theoretical math holds up against operational field audits, comparing standard tank mixes directly against the aqua-written nanoprotocol. Look at this data for a 3-acre block of primary putting surfaces. The annual baseline requires 329 pounds of traditional nitrogen. Under the nanoprotocol, that drops to a total of 1.05 ounces. Across a 30-acre fairway block, the math scales. The standard 3,920-pound synthetic nitrogen load is entirely replaced by exactly 10 ounces of precise biological input. The immediate question for any professional is whether removing thousands of pounds of fertilizer triggers a collapse in the physical playing surface. This performance table from the audit confirms that the surfaces maintain parity in overall turf quality and health indexed. In fact, specific physical metrics improve. Smoothness consistency increases by nearly 22%, and green speed rises slightly by over 4%. More notably, surface firmness under the extreme low nitrogen protocol actually increases by 4.5%. Delivering these results at precisely measured fractional rates also generates a transparent audit trail for facilities navigating increasingly strict environmental reporting requirements. The operational data confirms that high-volume nitrogen loading is largely disconnected from the actual metrics that define a premium playing surface. The measurable increase in surface firmness is the direct result of eliminating nitrogen-induced surge growth. This microscopic view explains the biology. Heavy nitrogen forces turf to grow rapidly, creating elongated, bloated cells that easily compress under weight. The nanotechnology protocol replaces that nitrogen with micronized silica, fortifying the plant's epidermal cell walls to create a rigid, interlocking structural architecture. Upgrading the plant's internal cellular rigidity is a requirement for any facility planning to implement operational electrification and autonomous equipment. Robotic mowers do not function well when removing bulk biomass. They demand highly consistent turf density and a perfectly upright growth habit to achieve a clean clip. Soft, nitrogen-heavy turf snags in the blades, laying over and mashing down. This mechanical friction drains electric battery cycles and leaves an uneven surface. The micronized silica provides the extreme drought resilience and wear tolerance necessary to withstand the continuous mechanical stress of 24/7 robotic traffic. Transitioning to autonomous infrastructure requires a biological foundation that can support the hardware. We can apply this identical model of precision efficiency to the most heavily utilized resource on the property, water, and the wetting agents required to manage it. Legacy moisture management relies on 55-gallon drums of bulk surfactants. Because of their viscosity, these chemicals require significant labor and immediate, heavy irrigation cycles just to flush them into the soil profile. The aqua-written Spark protocol utilizes nanoscale surfactants that move rapidly through the soil profile, removing the requirement for heavy flushing. The physical inventory drop is significant. For a 30-acre fairway block, annual fluid volume drops from 735 gallons of traditional surfactant to just 17 gallons. This timeline charts volumetric water content during a summer drought period. Despite applying a fraction of the product, the precision surfactant maintains an identical 16% moisture parity with the market-leading high-volume alternatives. By stabilizing root zone moisture at this exact level, the product prevents the steep drops in hydration, known as the afternoon wilt window. Eliminating those extreme stress periods removes the labor-intensive requirement for maintenance crews to perform emergency afternoon hand watering across the property. Surviving drought volatility is a matter of high-velocity hydraulic distribution, not simply overwhelming the soil with sheer volume. High-volume chemical reliance also creates property-wide consequences downstream. Nitrogen and phosphorus that leach past the turf eventually run off into the facility's water features. Once in the ponds, this nutrient overload fuels aggressive algal blooms. As the algae decays, it rapidly consumes dissolved oxygen, creating a dead anaerobic sludge layer at the bottom. This diagram shows the true cost of that runoff. Anaerobic decomposition in the sediment layer produces methane, a greenhouse gas 25 times more potent than carbon dioxide. Unmanaged, these water features act as carbon liabilities, offsetting any sustainability gains made elsewhere on the property. The biological correction involves treating the water to stimulate populations of native diatoms. These microscopic organisms bloom and rapidly consume the excess phosphorus and CO2 as their primary fuel source, starving out the nuisance algae. Once the diatoms consume those nutrients, they die and physically sink. Their silica shells ensure that the carbon they absorbed is permanently locked into the sediment layer at the bottom of the pond. This process physically transforms a toxic environmental liability into an active, verifiable carbon sequestration asset. Fourth-generation nanotechnology optimizes the biological efficiency of the entire property, from the cellular architecture of the turf to the dissolved oxygen in the water. The financial outcome of this efficiency is a major cost reduction. Facilities recover tens of thousands of dollars annually by insulating their operations from fertilizer market volatility and cutting direct expenditures on bulk surfactants. That recovered capital and optimized labor can be systematically reallocated directly into the facility, funding essential long-term infrastructure upgrades and autonomous technology. Transitioning to molecular precision guarantees a biological standard that protects the operational budget, secures environmental compliance, and permanently sustains tour-quality playing surfaces.